So good morning, everyone. Today we present the recitation lab for week 8 for Math 102. So I share with you my presentation first. Here it is. Okay. So our presentation today is about volumes using what we call the method, the disks method or the washers method, which are mainly in sections 7.2 and 7.3. We'll see two examples together, and we'll finish with an exercise for next week. So our first example is from Stewart's calculus book. And here they ask us to find the volume obtained if we rotate the region that is bounded by the curves y equals x squared and x equals y squared about the line y equals 1. We'll start first of all by sketching the region, of course. And to do so, you already have the week 7 volumes by disks and washers. 5, IP and B, you could use with the Jupyter Notebook. We start by importing the useful packages and functions needed as usual, as we did before for the 6 previous weeks. And let's do it together. So first of all, we define the variables x and y using symbols as usual from SymPy. And you notice here that x and y, of course, need to be real numbers. And we plot the graph of the first and second curve. Here are the commands. For example, 1, x and y as symbols. As you see here, we plot P1 as the plot of y equals x squared, P2 the plot of x equals y squared. You can see the plot of y equals x squared below the command window, and the plot of x equals y squared on the right of the command window. And what we could do also is to put the two plots over each other's using the extend function, and we can display both of the graphs together. So for the next slide, we can see the intended region, which is between bounded by the two curves. Here it is. Okay, so basically we're talking about this region here between the two curves, which would be rotated around or about the axis y equals 1, which would pass through this point of intersection. Okay, so one of the main things one could do is, first of all, to identify the region of interest. And you could notice that the values of x would be limited to be between 0 and 2 in the horizontal plot. And the third graph showed also the y equals 1 axis. So here we'll use the plot implicit. We define the new plot, let's call it P3, where it has that has these conditions, that y is above x squared, x is above y squared, and with x between 0 and 2, we'll have this full dimension. And of course, we'll also plot the axis y equals 1 using this implicit plotting. And here is our region, and here is the axis y equals 1. Okay, so now we are ready to start the integration. One can notice that the inner radius of rotation, or the closest one, would be given by 1 minus root x. 1 minus root x, because this is the upper part of the region, is the root x function, or the one that is closest to the axis y equals 1. Okay, and the outer radius of rotation would be 1 minus x squared, because the x squared curve, the y equals x squared curve, is the furthest from the axis y equals 1. So the volume formula would then be the integral from a to b, from the limits of the region, of pi r out squared minus r inner squared dx. And the limits of integration A and B are obtained by the solving the intersection equation, the intersection of the two curves equation. To do so, we solve the intersection using the solve method or the solve command. Intersection of y minus x squared with y squared minus x with respect to x and y, and we display the solution as we did before in previous sessions. So here we see that we have 2 points of intersections, which are the points 0, 0 and 1, 1. Okay, and since the rotation is with respect to y equals 1, which is a kind of horizontal axis, of course, the integration would be with respect to x. So basically, here is the point 0, 0, here is the point 1, and we'll integrate with respect to x. So the limits of integration would be with respect to x, and which means that we'll integrate from 0 to 1 with respect to x, r out squared, so the outer radius squared minus the inner radius squared, all multiplying by pi to get the volume. Okay, so now that you understood this, we can just compute the integral. So we are all set. We are all now set to get the volume, and we define r out and r in to be able to proceed. Here is the definition. R in would be 1 minus the square root of x. R out would be 1 minus x squared. And the volume would be pi minus the integral using the integrate command of r out squared minus rn squared. And x is the variable of integration. And the limits on the integration would be from 0 to 1. And we'll display the volume. Okay, so now that we are all set, here is our solution. It's going to be 11 pi over 30. Okay, hopefully it's clear. We have a second example also within these slides. The second example has a different function. Here, it's also extracted from Stewart's calculus book, and we are asked to find the volume of the solid obtained by rotating the region bounded by the curves 2x equals y squared, x equals 0, y equals 4 about the y-axis. So now we have a vertical axis of rotation. So how do we solve this? We first start by plotting the graphs. This is the horizontal axis y equals 4. This is here, this curve is 2x equals y squared. So basically it means that x is equal to y squared over 2. And of course the axis x equals 0. X equals 0 is the vertical axis or the y-axis. Here is a first sketch of our region. Okay, and then we will use the implicit plot to visualize much better to the region of integration. And here P3 is the implicit plot or plot implicit command of the region bounded by y less than 4, y squared minus 2x greater than 0. So we are above this graph, y greater than 0, x equals 0, and we'll take it in purpose such that x is between 0 and 8. So when x is between 0 and 8, here we have a full coverage of the region of integration. Okay, so this is our region. We intend to make it rotate about the y-axis. So now that we are all set, we understand that since we are having a vertical rotation, the integration would be with respect to the y variable. So we'll use the disk method, and here is the formula we'll use with respect to y. So the volume would be pi times the integral from c to d, r squared dy, and c and d would be the maximum values and the minimum values for y on this region. For sure here, the minimum value given this region is y equals 0, and the maximum value is y equals 4. Okay, so the radius of rotation, of course, is r equals y squared over 2. Okay, and here the volume is obtained by pi times the integral of r squared, the integral of r squared from 0 to 4 with respect to y. So here we get, of course, we'll get 256 pi over 5. Okay, so with these two examples, we've seen a rotation with respect to a horizontal axis, which was in the first example y equals 1, and with respect to a vertical axis, x equals 0, or the y-axis for the second example. We have now seen two methods. So for next week's presentation, we have this example where we are asked to use the method of cylindrical shells to find the volume generated by rotating the region bounded by the curves y equals e to the power minus x squared, y equals 0, x equals 0, x equals 1 about the y-axis. So here it is for week 8 presentation, a short presentation, and we'll continue with week 9. Thank you very much.